You are able to see my screen, right? Sort of, are you able to see my screen?
Yes, sir. It's visible.
Okay. So let us start with the first question for today. Okay. So this is the first question. Okay. So the thing is, I would give you 5 minutes time to solve the question, and then I would ask you what answer you are getting. So there is open loop transfer function for a DC motor. The omega is the speed of the motor, and VA is the uh, armature terminal voltage, and the transfer function is given over here. Okay. So, and it has been told that this motor, which is actually acting as a plant, this motor is actually connected in a unity feedback loop, as you can see on the diagram that has been given in the question. So, what is asked to you is what should be the value of K that would reduce the time constant of the closed loop system by 100 times as compared to the open loop system. This is open loop system or the plant, and I want to choose a value of K so that the time constant of the closed loop system becomes 100 times of the time constant of the open loop system. So you need to choose the correct answer. I'm giving you 5 minutes time to solve. So it is 7:05 now. I would ask you at 7:10. If somebody had, I mean, when you complete solving the question, you can just, unmute yourself and say that you have already solved it, and we will discuss. Anybody with this solution yet?
So D.
Anybody else with this with any other answer? Now, Kirti, can you explain why you are getting D?
So KA will be multiplied. So the standard form is given that 1 plus 10s, it is the time constant T is 10.
Right.
So it to be reduced by 100, we will get 0.1. But I didn't know how to solve this to get 0.1, so I just said D.
So you know these are time constant form, right? These are time constant form.
Yes, sir.
So this is the time constant of the open loop system. 10 seconds is the time constant of the open loop system, correct?
Yes, sir.
So what are you interested to find next? You are interested to find the time constant of the closed loop system, right?
It's a function of this system.
Time constant of the closed loop system. So
Yes.
so can you find the expression for time constant of the closed loop system? How will you do that? How would you find an expression for the time constant of the open loop system or closed loop system?
So we usually do GS plus 1.
Yes.
So after solving that, we will get our closed loop system.
Okay, so you first try to write the closed loop transfer function. Okay, GS divided by 1 plus GSHS that you have just told is the unit feedback. So GS divided by 1 plus GS, right? So for people who already know that this is a time constant form, so this is the plant that we are concerned about, and we have attached a P controller, proportional controller in cascade with the plant for controlling the plant. So so the time constant of the plant is this 10. You see, this is how we write a transfer function in a time constant form. So directly you can just see that time constant of the plant is 10 seconds. So now where you are getting stuck is the closed loop transfer function, a closed loop time constant. So the simplest way would be just write the closed loop transfer function. So GS divided by 1 plus GS would give you the closed loop transfer function. So if you compute this, what you are getting, 10k divided by 1 plus 10s plus 10k. So now Kirti, now tell me from here, how can you find the time constant? From this expression of the closed loop transfer function, how can you get the time constant of the closed loop function? You already know it.
Sir, the standard form is 1 plus TS plus.
Yes. So can you write this in standard form, in the time constant form?
Sir, there is no S. Yes, sir.
Yes. Tell me then how to do that.
So 1 plus 10 plus 10 into KA plus
Yes.
10S, and then taking 10 common from S. No, sir.
Okay, just see what would happen if you take 10k plus 1 common. See, can you not write it like this? So if you take 1 plus 10k as common from the denominator, you get this, right?
Yes, sir.
So now this is the time constant of the closed loop system, right?
Yes, sir.
So now it is in standard form. So the time constant of the closed loop system is this 10 divided by 1 plus 10k. You have got an expression for the time constant of the closed loop system. Now, according to the question, what your objective is to make this time constant 100 time of the time constant of the plant. Plant time constant you have already found to be 10. 10 divided by 100 is 1 by 10. So you equate this and you get k equal to 10. So the correct answer is C. It is not 100. You said it is D, right? Of Kirti?
Yes, so without solving, I just.
Okay. No, try to solve this because your guess marks would lead to negative marking. Try to reduce your mistakes. Whatever you do in gate, do it correctly or you don't do it. Okay, do not do this guesswork stuff.
Okay, sir.
Okay, then let us move on to the next question. Okay, so a op-amp circuit has been given to you. Op-amp circuitry has been given to you, and you need to find the output, the voltage at this terminal. That is the output voltage, V out. So the input voltage is minus 2 volt. This is plus 1 volt applied to the positive terminal, and you need to find V out. So you are asked to assume all the op-amps that you see in the circuit as ideal and find the V out. So I will give you again 5 minutes time. At 7:20 I would be asking you what answer you are getting. If anybody solves it before time, then you can unmute yourself, or you can just type in chat window that you have already done and what answer you think it would be. Anybody with the answer yet? It is already 7:20.
No, sir.
Anybody else? Saurav or Anu?
No, sir.
Okay. Anu, what about you? Why is people from electrical engineering are afraid of these analog circuits? These are very simple sum. I mean, I don't feel there is anything difficult in it. I would. Can any Navkirti, what is the problem that you are facing in this sum? If you could briefly explain. Yes.
It has given these op amps are biased at like plus 15 volt and minus 15 volt.
Yes.
So I'm just not able to figure out what will be the voltage
So
or it will.
what this biasing voltages have? What impact does this biasing voltage have on your output voltage?
Yes, sir. Yes, sir. Like plus 1 volt was at 1 kilo ohm, so there no current flows through the op amp. So I consider plus 1 volt. Then at the minus 2 volt and after 1 kilo ohm resistor, I consider to be plus 1 volt. So then we will get minus 1 volt at that point. But after that, I was not able to figure out how to solve it.
Okay. Okay. Now regarding this biasing voltage, okay, let me just clear a few concepts because there are several people making a few mistakes in this kind of sums. I will just tell you. So this is a circuit model of a op amp. Have you ever seen this? So this is the inverting input terminal. There is a negative terminal that you see. That is this negative terminal, and there is a positive terminal. So there is a positive terminal I'm talking about. So there is a positive terminal. Okay, and what we can, how we can model it is, I am saying that it is offering an impedance Zin. This Zin is between these two terminals, and what we are saying is this Zin is very high. If this Zin is tending to infinity, then the current, which is indicated in blue ink, you can see the current direction, that would be 0 because Zin, I am saying it is infinity, that is, it is open circuited. So that is how we say that this op amp is offering high input impedance to the the op amp is offering high input impedance, so the current drawn by it is almost tending to 0. Okay, anyways, but this at the output terminal there is a impedance Z out which is very low. Because why do we want the output impedance to be very low? Because if the output impedance is high, then most of the voltage drop would appear across this Z out. Okay, and the output voltage you would get is very low. So what we want is this output impedance, we want it to be very low. Okay, now you see there is an amplification factor A into V2 minus V1. So this difference in voltage, that VDIF, is being amplified over here. And if I neglect this Z out, I will say that Z out is very small and the voltage drop across it is very small. Then we can say that V out is nothing but A into V2 minus V1. So we can say that V out is equal to A into V2 minus V1. So what is V2 minus V1? That is V out divided by A. And as it is an ideal op amp, we are saying that gain is infinite. And therefore, as A tends to infinity, V2 minus V1 is tending to 0. If V2 minus V1 is tending to 0, that means V1 and V2 are almost in same potential. Okay. But please keep in mind, this is the concept of virtual short. But please keep in mind, do not blindly apply this concept everywhere. Okay. This is valid only when the op amp is operating in the linear region. That is why I have indicated the VI characteristics of an op amp. You see, when the op amp is in this linear region, then only can you write this equation. If the op amp is in this region, then only can you write this equation, and then only can you say that V1 is almost equal to V2 because A is very high. What does A mean? That is the slope of this line. This slope is not drawn to scale in this figure. in practical case, this would be very high. I mean, this slope is very steep. It would not be so, slope is not so low. It would be very steep. It would be like this maybe. I mean, I do not have a pen or something. Do I? A pen. So it may be something like, okay, it is not writing. Okay, so let me just a minute. Anyways, I've just changed this thing. Okay, I'm back. So the slope would be in practical case, it would be very steep. Okay, somewhat like this. I have a thicker pen over here. Maybe you can just imagine it to be a thinner line. So what I'm attempting to say is that the slope may not be such high slope over as I've shown in the curve. It is not drawn to the scale. I have just drawn this to make you understand so that things become a bit more clear, or else it may appear very straight, as similar to that of the y-axis. It would be very steep curve, okay, just like the one that I've drawn over here. So as long as you're operating in this region, as long as you're in the linear region, then only can you apply this concept. If you are not in this linear region, then you cannot say that this concept is valid. Okay, so that is one point you have to keep in mind. Now the biasing voltage. So when you move to the saturation region, you are no longer in this linear region. When can that happen? Say you have a capacitor across this terminal and this output terminal, and you find that the voltage across the capacitor plus this voltage becomes greater than the Vsat voltage. Then you have moved from the linear region to the saturation region. In the saturation region, you cannot say that this concept is valid. Okay, so before applying this virtual short concept or virtual ground concept, you have to check whether you are operating in the linear region. If you are operating if you have a positive feedback, or you are operating the op amp as a Schmidt trigger, then you cannot apply this concept, because in that case you are operating in the saturation region or not operating in the linear region. See, when you are using op amp as a comparator, when you are giving some voltage at V1 and a reference voltage at V2, when you're using the op amp as a comparator, then the output of the op amp is either plus Vsat or minus Vsat, which means you are not in linear region, you are in the saturation region. Your operation is in saturation region. Similarly, when you're operating this op amp as a Schmidt trigger, the output is similar. The output would be either plus Vsat or minus Vsat. That means you are operating in saturation region. So first check in the question whether you have a positive feedback in the op amp that you have at hand, or whether there is a capacitor which is which saturating the output voltage. No such case is there, no such complications are here in the question. There are simple resistors over here. So I couldn't find, what is the, why it was so tough. Okay, so first you have to keep in mind whenever you apply this concept, you have to make sure that the op amp is operating in linear region, not in saturation region. You have to check it in the question. Whatever question has been given to you, you first check whether positive feedback is given to it, or whether there is a capacitor which moves it to the saturation region, and there is a specific name for this. There are controllers where we use this PI controller. There is a problem with PI controller, which I have already told in maybe in the previous session. So there is something called anti-wind up. Okay, the capacitor saturates and it remains in saturation region. So there is a problem with that configuration with the PI controllers. So this is something that you have to keep in mind while you analyze this kind of op amp circuit. And this is something which I have already explained to you. The ZIN I want to be very high, because I do not want the device to draw any current from the the voltages this terminal. Maybe you are comparing something, so maybe there is a potential divider over here, and you are connecting this point to some potential divider. So if this ZIN is low, then current would be flowing through this terminal and you would have loading effect. So you understand that if the current ZIN is high, then there will be loading effect and you would not be able to measure the voltage correctly at this point. So say there is a resistance, the potential, say you are measuring some 5 volt and you have connected a potential divider 2.5 and 2.5. Okay, you want 2.5 volt to be given to some comparator. So if this ZIN is very low, this ZIN would come across this 2.2 ohms potential divider, and the voltage that you are applying over here would not be 2.5 volt, it would be somewhat less than that. So that is what we call is a loading effect. Okay, so we do not want the op amp to have any loading effect. So what I want is I want the ZIN to be very high, therefore so that it doesn't draw any current from the point where I want to measure the voltage. Okay, so what I ideally want is ZIN to be very high and Z out to be very low, because I do not want any voltage drop across Z out, so that I can get A into V2 minus V1 at the output. That is the basic fundamental of a op amp operation. Okay, now look at the question that has been given to us. Okay, so Navkirti, you have already told me that you know that the op amp imposes infinite impedance to the input terminals. So the device current, that is ID1 and ID2, are equal to 0. That is why what is the potential at point B? It has to be 1 volt, because there is no potential drop across this 1 kilo ohm. If there is no potential drop across this 1 kilo ohm and this point is electrically connected to this point, then the potential at this point must be 1 volt. So because of again virtual short concept, because there is no positive feedback or any capacitor across it which can cause that problem, so there is no need for checking it. So the potential at point B is same as potential at point A. So what is the potential at point B? That is 1 volt. What is the potential at point A? That is 1 volt. Now tell me, Navkirti, what do you think is the direction of current I1? Would it be opposite of what I have indicated over here, or would it be in the same direction I have indicated in the picture?
So as current flows from high potential to low, so it will be in the same direction of I1.
Correct, absolutely correct. So if that is so, then and ID1 is 0, then I2 must be flowing in this direction. Because if we apply KCL, you say there is no current flowing through this path, ID1 is 0, you are saying. That means the current must flow in this direction and I1 must be equal to I2. So if I1 is equal to I2, then potential at V01 would be the potential at this point plus the potential drop across this 1 kilo ohm. Right? Because V01 must be at a higher potential. As current is flowing from this point to this point, it must be at a higher potential. So if it is a higher potential, so potential at point A plus this potential would give you potential V01. Okay, so this is what I have done. You will find that. So what is I1 then? So potential at point A is 1 volt. So 1 minus of minus 2 volt, that is 1 plus 2 volt divided by 1 kilo ohm would give you current I1. So I1 is equal to I2. So what is the potential drop across this 1 kilo ohm? That is 3 milliampere into 1 kilo ohm, that is 3 volts. Okay, and what is the potential at this point? That is 1 volt. So 3 plus 1 volt, and the potential at this point must be 4 volt. So if potential at point 01 or O1 that I have indicated over here as VO1 has been determined now as 4 volt. Now we can just analyze this circuit. There is nothing much to it. It is just a negative feedback with the positive voltage applied at its non-inverting terminal. Okay. So one important point again to notice, this 4 volt that you have got is less than plus 15 VSAT volt. So there is no question of saturation at all in this. So if that is the case, then let us look at what is output voltage for this part of the circuit. So this is a simple negative feedback op amp circuitry with the positive voltage VO1 applied at the non-inverting terminal, the output voltage in such a case is given by 1 plus Rf divided by R. What is Rf? 1 kilo. What is R1? 1 kilo. So that is 2 into 4 volts, because V01 I have found out to be 4 volts. So we multiply this 2, we get 8 volt. So that is the basic way of doing it. It is a very simple sum. Now, can you tell me what is a typical input impedance offered by an op amp?
So
What?
ideal op-amp,
Yes, yes.
infinite size.
Not ideal, a typical, value of a, if you take a op amp data sheet, what is the typical value of this input impedance offered by a op amp IC?
So maybe in mega ohms or kilo ohms.
Right, it is in few of mega ohms. So you have to keep in mind that the resistance that you connect, that is much lower than that. So if this is in mega ohms and you are also connecting a resistance of some few mega ohms, then you cannot make this assumption that ID1 0 and ID2 0. Then you cannot make that assumption. You have to take into consideration the input bias current and all. So this is another practical consideration that you have to keep in mind while designing a circuit or while analyzing a circuit. You also have to keep in mind the resistance that we are connecting, that must not be of the same order as that of the input impedance of the op amp. That is another thing that you have to keep in mind. For all the analysis, all the assumptions that we make, then all these assumptions that we make won't be true. So these are a few things that you have to keep in mind while solving this op amp circuitry. Okay, so now let us move on to the next question. Okay. Okay, so this is the next question. Is a very simple question. A periodic voltage waveform has been given to you, and the one cycle of the voltage waveform is given to you over here, and a PAMC permanent magnet moving coil meter is connected across the same load terminals across which the oscilloscopes this kind of a waveform, and what you need to find is the reading of a PMMC meter. So let me give you another 5 minutes to solve it. It is 7:37. Okay, I would ask you after 5 minutes. Oh, sorry. If anybody has already solved the question, you can just Type in the chat window, or you can just say that you have completed.
Sir, C.
C is 8 volts. Okay. How are you saying? Is it is C?
Sir, PMMC will measure average of this waveform. So after calculating it, I got C.
Okay. Okay. So this much you know, that PMC would give you an average of the voltage waveform, right? This much is already known to you. So, so let us find the average value of this. What is the average value? What is the time period? Time period is 20, right? 20
Yes, sir.
milliseconds. So 1 by T into the shaded area. This area you need to find out. So half into base is 10, the height is 10. This gives you the area of the triangle minus of the area of this rectangle, because it is the negative area. It is, you see, it is below the x-axis, right? It is below the time axis, so it's a negative area. So you have to subtract it. You don't have to. I mean, it would be incorrect if you add it. You have to subtract it. So 5 into 2. So this is the area of this small rectangle that you see formed between this 10 and 12. So, and this area which is found between 12 and 20 would be 8. I mean, the time axis, the time width is 8 and the height is 5 volt. So what is the area of this rectangle? That is 8 into 5, and 10 to the power minus 3 I have written over here because of the time scale is in milliseconds. So if you do this operation, you will find 4 volts. Is it a calculation mistake, or you have done, you have
Yes, sir.
added
I
this?
forgot to divide it by the time period. So
Okay. But if you hadn't divided by time period, then you would have got some 10 to the minus 3 term. You haven't got that.
yes, sir, I just approximated it to 8.
Yeah, you are doing again guesswork. Don't do the guesswork. Just tell whatever you are getting. Okay. So let us move on to the next question then. It was a very simple question. Okay, now let us move on to this question. So the input output relationship of a system is given to you. That is yt equal to minus infinity to t x of tau cos 3 tau d tau. Okay. And you need to find out whether the system is time invariant, or is it stable or unstable. So four options are again given to you, and you need to find out the correct option. So I will give you 5 minutes again to solve, and then we will go ahead with the discussion. Anybody with the answer yet?
So it's stable, but
But
so D.
not time invariant and not stable. You said it is stable?
No, so it's also stable, stable,
Okay, stable. Then which one? Time invariant
and
A or
so time variant.
time variant? So B you are saying stable and not time invariant.
Yes, sir.
Okay. So why are you saying it is not time invariant?
So because output will vary with time, like minus infinity to t at different t.
What is the
There will be
definition of
different t.
convolution? What is the definition of convolution? Minus infinity to t, right? So convolution is applicable for time invariant systems also. So how by just looking at the limits you can say it is time varying? Something else you need to see. Tell me what else. What looking at the equation itself you can say it is time varying. But I want to point out what makes you say it is time varying.
So cos function.
So cos function then. So if it is cos of you know so if I put a cos of 3.25, would that be a time varying function?
Sir, we are
No, sir,
having
not.
Yes, tell me what is your doubt.
tau.
You are having tau, right? It is a function of time. So if yt was had only the term of x, I mean the input term, and then we would have said that it is time invariant system. But it is a time varying term multiplied with the input. Whenever you see in a question, you have a output relationship with a time varying term, you multiply it with the input term, then you can directly say that it is time varying. However, let us look at the formal procedure of we'll look at the formal procedure of doing it. And who said that? Was that Rahul? Who was it? Sort of, was that you?
Yes, sir, I am.
Okay, so what do you think about the stability of the system?
Sir, I am not aware of the stability of the system.
Okay. Any guess, or how how you can just give anything that's coming to your mind.
I think it's a stable system, sir, according to the limits.
According to the limits, it is a stable system, you think.
Yes, sir, it's just a guess.
So what makes you say that? Any logic behind it?
Sir, according to the limits, it's minus infinite to t. The term will be stable. It means the
So
time
how
is
do
Time
varying
you?
with.
variation will not give us infinity or any kind of value.
So how do you check the stability of a system? Sort of, how do you check stability of a system?
Sir, I don't know, sir. I have forgot it.
You have heard about BIBO, bounded input, bounded output stability.
Yes, sir. Yes, sir.
So what does that theorem says?
So for bounded input, output will be bounded.
Correct. What does bounded mean?
It will have a definite amount of input, not infinity.
Okay, so
For,
you want to say that a signal is bounded when it has a finite value at any instant in time. Correct?
yes, sir.
Okay, good. So you are saying it is a stable system. So it is never going to give you infinity. Okay, can you put x tau as cos of 3 tau and tell me what is the value that you are getting? Integrate it and tell me. It is a simple, class 12 mathematics. You put x of tau as cos of 3 tau and multiply that with cos of 3 tau, integrate it from minus infinity to t, and tell me what result you are getting. Have you integrated? Navkirti or Saurav?
So x by 2 plus sine 2x by
X by tau. I have asked you to substitute x of tau with cos of 3 tau. Where from are you getting x again? I
yes
have
sir.
asked, yes, I have asked you to replace x of tau, substitute x of tau with cos of 3 tau, and do the integration. Simple class 12 mathematics I am asking you to do. Sort of, what are you getting?
Yes, sir, I'm trying to calculate.
You can do that mentally. What are you trying? I mean, see, so if it is cos of 3 tau, it becomes cos square 3 tau d tau, right?
Yes, sir.
So you multiply with half, you in the outside, and you in the inside you multiply it with 2. So 2 into cos square 3 tau. So 2 into cos square 3 tau is, can you get that trigonometrical equations over there? 2 into cos square theta d theta, what can you write?
One plus cos 2 theta.
Yes. Then integrate that, what are you getting?
Tau plus sine 2 tau plus divided by 2
So what is the limits of the integration?
minus infinity to t
You replace tau with that, what are you getting?
minus in sir my sine infinity minus infinity is
Sine infinity is bounded, okay. What about this minus infinity term you are getting?
sir it is not bounded.
Okay, so you see it is not a stable system, it is an unstable system. Okay, so let us do it formally and I will just show you. Okay, so let us just test for time invariance first. So how do you test for time invariance? Let us first delay the output of the system. The expression that has been given to us is the expression given to us. Let us delay it by a amount t, okay, capital T. You see the t, the term t is over here, okay. All other terms are tau, okay. So when I am replacing t with t minus capital T, this t will also be replaced by t minus capital T. So y1 t minus capital T is equal to integration within the limits minus infinity to t minus capital T x of tau cos of 3 tau d tau, okay. Now let us now delay the input x of t by amount t, okay. So if we do that, we are only going to replace or delay this signal by amount t. So what I have written over here, x of t tau minus capital T cos of 3 tau d tau, correct. Now if it is a time invariant system, then if the input is delayed by a amount capital T, the output would also be delayed by a amount capital T, which would essentially mean that y1 t minus capital T would be equal to y2 of t if this system is time invariant. Okay, so now to see whether these two expressions are same or not, what I have done is, you see there is a single term inside the bracket, x, I mean within the x bracket there is only a single term. So what I have done is I have replaced this tau minus capital T with u. So you see I have put tau minus capital T u. So if I do that, so how can I replace 3 tau? So I have written tau from here. So tau equal to u plus capital T, multiply that with 3. So 3 into u plus capital T. You differentiate this equation, you get d tau equal to du. So you can replace this d tau with this d tau with this du, because d tau is equal to du. Now let us write the expression y2 of t in terms of u. You are just eliminating this this tau term and you are writing in terms of u. Okay, so if you do that, so what do you get? You can write x of u cos of 3 u plus capital T du. And what about the limits? We have already seen that u equal to tau minus capital T. When tau is minus infinity, u is also minus infinity. When tau is t minus capital T, u would be t minus capital T. Okay, so just a minute, what it is? When tau is t, small t, sorry, not t minus capital T. When tau is small t, then u would be t minus capital T, which I have already written over here. So the limits, if I substitute all the tau with u, would be from minus infinity to t minus capital T. And from these two expressions, expression 3 and equation 1, we find that these two expressions are not same. So it is time varying. Is this much clear to everybody, or was I too fast?
Clear, sir.
Sort of, was I clear or was I too fast?
Clear, sir.
Okay. So talking about the stability, as I have already told you, you have just put cos of 3t. So cos squared, okay? You put half outside, 2 on the inside. So that is 1 minus cos 2 theta, right? So 1 minus cos of 6t. So if you integrate that, d tau would be tau and cos term would be giving you, this would be integration of cos would be plus sine 6t. So tau minus sine 6 tau divided by 6 within the limits minus infinity to t. So now you see there is this t, if we replace that with minus infinity, this entire term goes to minus infinity. So the system is not stable, because even if we give a bounded input, it is giving a unbounded output. Okay, the correct option is D. Okay. So was this clear, sort of?
Yes, sir.
Okay. Just a minute. Okay, this would be the last sum for today. Okay, this I intended to do, I mean, day before, I mean, the week I took the class last, but I couldn't find time. Let us do it and then I will stop. Okay, so a transistor has been given to you. I think Anu has already done it. Anu, you can leave if you have some other task or essential tasks to be completed. I am discussing the same thing that I have discussed with you. I think you are the only one who was present in the class when I discussed this. I'm just repeating this because for the sake of others. Okay, so a transistor BJT circuit has been given to you, and it has been told that VC is sat, that is the collector to emitter voltage at saturation would be 0.2 volt, and VB is 0.7 volt, that is base to emitter is 0.7 volt. what is the maximum value of RC, this resistance, there is a collector resistance RC, such that the transistor is always in the active region. Okay, you need to find the maximum value of RC so that it is always in this active region. So I'm giving you 5 minutes time to solve, and then I would ask you how you are solving it. Anybody with the answer yet?
Sir, 1 minute is done with the calculation.
Okay.
Sir, 0.225 ohms.
0.225 ohms. Tell me the approach that you are taking.
So IC is equal to beta IB. So I took IC as 5 minus 0.2 divided by RC is equal to beta given, and
5
2.
minus 0.2.
Yes,
What is
yes, sir.
0.2 volt?
So
What is
VC,
this?
so saturation voltage.
That is VCE, right? That is
Yes,
collector to emitter voltage.
emitter voltage. Yes, sir.
5 minus 0.2 divided by,
So RC for collector current.
tell me what is the base current.
So 2.15 into 10 raised to power
No,
minus
not the
3.
values. Tell me the procedure for finding the base current.
So I just applied KVL in this loop, 5 volt, RS 2 kilo
Yes.
ohm, and VBE 0.7 volt.
Yeah, so 5 minus 0.7 divided by 2 kilo ohm.
Yes, sir.
Okay, so that is the base current, right?
Yes, sir.
So now you are saying beta into IB would be the collector current,
Yes, sir.
correct?
Yes, sir.
So what is the value of the collector current?
So 5 minus VCE, that is 0.2 divided by RC.
5, why 5 then?
So other side
Okay, okay,
5
you are
minus.
saying this loop, right? You are saying this loop.
Yes, sir.
Okay, 5 minus 0.2 divided by RC into beta is your this current. Okay, then
So then equating them and finding RC.
equating what? Acha. Acha, you have to, okay. So you have found RC to be
225.
0.225 ohms.
Yes, sir.
That is a pretty let's see. I mean, I forgot the answer myself. I would just do the calculations then. Okay. So tell me, so why, I mean, can you tell me what is actually happening? Why changing the value of RC would make this BJT go into saturation? Can you tell me what is the problem happening over here? Let me move to the next slide. So I am saying that RC is a variable resistance, and it is a potential, potential divider, what we say, potentiometer. Okay, and I am varying RC. Okay, so can you tell me what is the problem which drives this VC into, which drives this BJT into saturation? What is happening over here? I have written it over here also. Okay, let me just say it then. So what I am saying is this, again, this IC equal to beta into IB, this relationship is valid only when this transistor is in active region. In the second step, you have replaced VCE by 0.2, which means the BJT has gone into saturation region. In one part you are using this relation, in another part you are using VC is 0.2. Can you tell me why can you do that?
Yes,
What?
sir.
Yes. Why are you doing it?
If it is in.
It is in the boundary condition. It is just at the boundary of saturation and active region. That is why we can do it. Getting my
Okay, sir.
point?
Yes, sir. I didn't know that.
Yeah. So it is in the boundary condition. I mean, it is at the boundary of active region and saturation region. Okay. So let us first assume that it is in the active region. Okay. So let us first assume that it is in the active region. In active region, okay, let me just give you one one thing to solve. Let me say that IC is 0.215 ampere. Okay, you have already found this out, 0.215 ampere.
Yes, sir.
Okay, now say this RC is 200 kilo ohm. Okay, this RC I am saying it is 200 kilo ohm. Can you tell me what VC would be? You see, at any cost, this current IB is constant because KVL in this loop has to be constant. I mean, has to give a constant value. 5, this voltage is not changing, VB is not changing. So 5 minus 0.7 divided by 2 kilo ohm is constant, IB is constant. So the only thing that I am doing is I am changing the resistance RC. Okay. So if it is an active region, IB is constant, beta into IB would also be constant, that is IC is also constant. And as I am increasing RC, the voltage drop, that is VC, I have indicated by a pink colored in this diagram, VC keeps on increasing, correct? If RC, if I keep on increasing, keeping IB constant, that is IC constant, VC keeps on increasing, correct?
Yes, sir.
Okay, so now do this simple sum. What you do is in this you apply a KVL in this loop and tell me if this RC, if I have kept it to be 200 kilo ohm, what would be the VC? Just a subtraction, just tell me quickly. 5 volt minus IC into RC. IC I have told it to be 0.215, RC is 200 kilo ohm. Use a calculator, tell me quickly. What is the value you are getting?
Sorry, it's 42.99.
What is the polarity?
It's negative, sir.
Negative. Is it possible?
No, sir.
Why are you saying that? Why are you saying that? Sort of.
So because in VB IB is almost constant, so for it to be act as a switch, VC must be around 0.
Correct, but why is it not possible that VC is negative? That is what I was asking. So see, if it is negative, that means you are saying IC is flowing, and you are saying the voltage drop across is negative. That means the current must flow in the opposite direction. However, this would allow BJT would allow current flow in a particular direction, which is indicated by the arrow. So it is not possible for VC to go negative. So as you increase RC, this voltage VC keeps on increasing. To keep VC plus VC constant, to keep this value plus this value constant according to KVL in this loop, what would happen is this voltage VC would keep on decreasing, correct?
Yes, sir.
VC plus VCE is 5 volt. By increasing the resistance RC, keeping IB constant, what I am doing is I am increasing this potential drop. IC into RC potential drop is increasing. As a result, as this summation of these two is constant, if this term increases, then the other term must decrease. That means the voltage across this collector to emitter terminal is decreasing, and it keeps on decreasing and goes to a particular value which is given to you question as 0.2 volts. Okay, it is a saturation value. That means after it reaches this value, the voltage across this becomes constant, that is 0.2. It has started to act as a switch. The power BJT you have already studied in power electronics. This is how we operate this as a switch. During on state, the voltage drop is very low and the power loss would be, the conduction loss is low. That is the basic philosophy. So what I'm trying to say is, just by varying the resistance, we are actually pushing this transistor or BJT into saturation. Okay, so the voltage across the collector to emitter keeps on reducing, and the moment it reaches 0.2, it remains constant, and then we can say that it has gone into saturation. So in order to make sure that the BJT is in active region, you have to choose the value of RC very carefully. Okay, that is all that you have to do. So we have already found IC, and we already know that VC is 0.2. So, and the only thing that we are left to find is the value of RC. So 5 minus 0.2 divided by IC, that is the value that we have got. So if you do that, 5 minus 0.2 divided by 0.215, that is 22.32 ohms. So this is the answer. Navkirti, what was the saying? 0 point something you said, right?
Yes, sir. Maybe some calculation mistake.
So you are already at the age of the exam. Don't do this kind of a mistake. Then it will be a problem. Okay. So it is already 8:22. I was planning to stop the session over here. Anybody has any question, or anybody wants to say anything?
Sir, in next session, can you please discuss the like switching characteristics of BJT and IGBT?
Switching characteristics of BJT and IGBT. Next session, actually, we are actually assigned something to teach you people. It is I do not know. I cannot make a promise because my father is not well and I have to go again another time for a surgery one more time. I'm not sure whether I can keep that promise. Uh, I do not think I would be able to do that because this January month is too much hectic for me this year. Teaching you IGBT and
No, sir, it's okay.
it would be difficult for me now, but yeah, because on 26th I would be leaving again because my father has to go through another surgery. First surgery has already been done. So maybe on 26th I have to reschedule my class. I have to tell these NPTEL people to reschedule my class of 26 to some other, 27 to some other, because my father's surgery is planned on 27th of January. So maybe on 27th of January I won't be able to take a class. I would be taking class maybe on some other day. This the NPTEL people would tell you when this would be when this class would be rescheduled. The class on 27th. That is one thing. Another thing is they told me to mention you people that they are holding this mock test every Sunday or something. I'm not sure exactly about the date when they are.
Yes,
taking
sir, we
it.
have been told in other lectures as well. On
Okay,
Sunday,
okay.
sir.
Okay, good. So they told me to convey this to you people, so you can just try and solve those questions which they are giving in mock test. Switching characteristics. It is very interesting. Switching characteristics of IGBT. I would have been happy to teach that, but constraint of time and constraint of things that are happening with me right now is difficult for me to teach.
It's okay, sir. Hope your father get well soon.
Yeah, thank you very much. Sort of any questions from your side?
No, sir.
Okay, so let us end the session for today. We would meet again maybe on the next Friday. Thank you very much.
Thank you, sir.